Look up on a clear night, and you are looking at something that feels permanent. The same stars burned above every human who has ever lived, every war, every empire, every person you have ever loved. They will still be burning long after all of it is forgotten. That is the illusion. Every star overhead is a temporary arrangement of matter running down a clock that started 13.8 billion years ago. The universe is not waiting to end. It is ending right now, continuously, in a process already well underway. Physics allows several different ways for it to finish. Some take longer than there are words to describe. Some arrive on a schedule, in a few tens of billions of years. And one of them arrives with no schedule at all. No warning, no signal, nothing to see coming. That one may have already started. Nothing about tonight's sky would look any different if it had. Start with the ending physicists consider most likely. It is also the one that gives the most warning, more warning than the human mind can hold. In 1998, two independent teams measuring distant supernovae found something nobody expected. The expansion of the universe is not slowing down. It is speeding up. Something is pushing space apart. We call it dark energy, and the honest description of it is this. It is a name for a measurement we cannot yet explain. It accounts for roughly 68% of everything in the universe, and it appears to be a property of empty space itself, which creates a feedback loop with no exit. Expansion creates more space. More space contains more dark energy. More dark energy drives faster expansion. Run that forward. In about 100 billion years, every galaxy outside our own local group will have crossed beyond the horizon of what we can see. Not destroyed, simply carried away faster than their light can travel back. An astronomer alive then, looking outward with perfect instruments, would see a small island of stars surrounded by absolute black, and would have no way of ever discovering that a wider universe had once existed. The evidence of the Big Bang will be gone, not hidden, gone. Star formation runs down as the gas needed to build new stars is finally exhausted. The last red dwarfs burn on for tens of trillions of years in a universe with nothing left to illuminate, and somewhere around 100 trillion years, the last of them goes out. And what remains is cold, dark, and still expanding. But the big freeze is not finished. It has a final chapter, and it belongs to the only structures left. In 1974, Stephen Hawking showed on theoretical grounds that black holes should not be permanent. Quantum effects near the event horizon should cause them to radiate energy very slowly and therefore to lose mass. It is worth being clear, this radiation has never been detected. It is a prediction, not an observation. But it follows from physics we otherwise trust, and almost every physicist expects it is real. If it is, black holes die, and they die strangely. A shrinking black hole does not cool, it heats up. The smaller it gets, the faster it radiates, the smaller it gets, until the last moments when what has been the darkest object in the universe finishes in a burst of gamma radiation. A black hole the mass of the sun would take around 10 to the 67 years to evaporate. The supermassive giants at the centers of galaxies, closer to 10 to the 100. That number deserves a moment. 10 to the 100 is a 1 followed by 100 zeros. The total number of atoms in the observable universe is about 10 to the 80. If every single atom in existence were itself an entire universe full of atoms, you would still not have enough to count that high. And at the end of it, the last black hole exhales, and the universe contains nothing but a thin, cooling fog of particles drifting apart forever. There is one more thing that has to happen for that picture to be complete, and it is rarely mentioned. The matter itself has to go. Several attempts to unify the forces of physics predict that the proton, the particle at the heart of every atom in your body, is not stable. That given enough time, it simply falls apart. We have looked. Detectors buried under mountains have watched enormous tanks of water for decades, waiting for a single proton to die. None ever has. That failure sets a floor. In the decay channel we have watched most closely, a proton must last longer than 10 to the 34 years. So this one stays a hypothesis. It may be that protons are perfectly stable and matter persists indefinitely. But if they do decay, then somewhere far beyond the death of the last star, every remaining object, every cold planet, every burnt-out stellar core, every atom that was ever part of anything, quietly dissolves into radiation. Not destroyed by anything, just expired. That is the ending with the most warning. Trillions upon trillions of years of it. The next ones come with considerably less. Everything in Act 1 assumed dark energy stays as it is. There is no guarantee of that. And recently that assumption has started to look less safe. Large surveys mapping how dark energy has behaved across cosmic time have produced early results hinting that it may not be constant, that it may have been weakening. The signal currently sits at around 3 sigma, suggestive, not a discovery. These findings are preliminary, and they may not survive better data. But if they hold, they open a door that had been considered closed. Because if dark energy weakens enough, gravity wins. Expansion slows, stops, reverses. And a contracting universe is not simply the expansion played backwards, because everything inside it is still radiating. The cosmic microwave background, the cold afterglow of the Big Bang, currently a few degrees above absolute zero, gets compressed along with everything else. It heats up. There would come a point where the night sky itself glows. Then a point where the sky is hotter than the surfaces of stars, and stars begin to boil away from the outside in. Galaxies collide not because they drifted together, but because there is no longer room for them to be apart. And then everything that has ever existed is compressed back toward a single point. Some models put that on a timeline of roughly 20 billion years, which is a real number on a real clock. Longer than the universe has existed so far, but not by much. Now take the same uncertainty and push it the other way. The behavior of dark energy is captured by a number physicists call W. If W is exactly -1, dark energy is constant, and you get Act 1. If it is greater than -1, dark energy weakens as space expands. And if it weakens far enough or turns negative, gravity may eventually win. That is the big crunch. And if it is less than -1, if dark energy strengthens over time, you get something considerably worse. If dark energy is assumed to be constant, our best measurements put W extremely close to -1, with an uncertainty window that straddles the line. If it is allowed to change, the data lean toward a W that has crossed that line at some point in cosmic history. Either way, we cannot currently measure it precisely enough to know which side of it we are on now. Sit with that. The question of whether the universe freezes, collapses, or tears itself apart is at this moment an open measurement. If W is below -1, the acceleration itself accelerates, and the destruction arrives in a specific order, because it works its way down through scale, dismantling structures from the largest to the smallest as the expansion overwhelms each binding force in turn. Galaxy clusters are pulled apart first, then individual galaxies unravel, then solar systems, planets drifting away from their stars not by any impact, but because the space between them is growing faster than gravity can close it. Then stars themselves come apart, then planets. Then, in the final fraction of a second, the expansion exceeds the strength of the forces holding atoms together, and matter stops being matter. Some models that assume a strongly phantom W place this around 22 billion years from now. In that scenario, the last second of the universe is the only one in which anyone would notice anything was wrong. And by then, it is already inside the atoms of whoever is watching. Everything so far has been about how the universe stops. This one is about something more disturbing, the possibility that it does not. If the universe collapses, what happens at the center? Classical physics says a singularity, a point of infinite density where the equations stop producing meaningful answers. But some approaches to quantum gravity suggest that at extreme enough densities, gravity may become repulsive, that the collapse does not reach a point, that it bottoms out and rebounds. A new expansion, a new universe from the ashes of the old one. This remains speculative. There is no accepted theory of quantum gravity, and cyclic models face serious objections, the most stubborn being entropy, which should accumulate across cycles and leave signatures we do not see. But follow it anyway, because of where it leads. If the universe can bounce once, there is no obvious reason it can bounce only once, which means this may not be the first. It may not be the 1000th. There may be no first. Every ending described in this video would then have already happened, not once, but without limit. And in some versions, every configuration of matter that can occur would have occurred, possibly including this one, possibly including you, sitting exactly here, having exactly this thought. An infinite number of times, with no memory of any of them. That leads somewhere worse, and it is a problem physicists take seriously. Not because they believe it, but because they cannot cleanly escape it. In a universe that lasts long enough, random fluctuations will assemble anything that is physically possible. Given enough time, particles drifting in the dark will occasionally, by pure chance, arrange themselves into something ordered. Usually something trivial, but over the timescales in Act 1, the calculations suggest that fluctuations should eventually produce a conscious observer, complete with a set of memories of a life that never happened, which then dissolves back into the dark within moments. And here is the problem. In some models, those random observers vastly outnumber observers like us, who arose the ordinary way, which would make it overwhelmingly more likely, statistically, that any given observer is one of them, including this one. Most physicists treat this as a signal that something in the underlying model is wrong. The argument is generally used to rule theories out, not to describe reality. It is a reductio, not a prediction. But no one has produced a fully agreed way to make it go away. It sits there in the mathematics as an unresolved objection. Every ending so far has given the universe time, trillions of years, tens of billions. Even the Big Rip offers 22 billion. They all have a countdown. This one does not. In modern physics, empty space is not empty. It is filled with fields, and the values those fields settle into determine the laws that everything else obeys. The masses of particles, the strengths of forces, whether atoms can form at all. Those fields sit at their lowest available energy. That state is called the vacuum. The question is whether it is the lowest possible state or merely the lowest one nearby. A ball resting in a dip halfway down a hillside is stable until something nudges it over the edge. If our vacuum is that dip, a false vacuum, then the universe is not in its final configuration. It is in a temporary one. This stopped being purely abstract in 2012 when the Large Hadron Collider measured the mass of the Higgs boson. Combine that value with the measured mass of the top quark, run it through the standard model, and the calculations point to an uncomfortable answer. Our vacuum appears to be neither clearly stable nor clearly unstable, but sitting close to the boundary between them, a condition physicists call metastable. The result depends sensitively on those measured masses and on the assumption that no undiscovered physics intervenes at higher energies. It may well be wrong, but as our current best calculation, it says the vacuum is balanced on an edge. Stephen Hawking wrote that the Higgs potential has, in his words, a worrisome feature, that the universe could undergo catastrophic vacuum decay with a bubble of true vacuum expanding at the speed of light. It could happen at any time, he wrote, and we would not see it coming. If the vacuum tunnels to a lower state anywhere, one bubble, one point in space, that bubble expands outward at very close to the speed of light. And inside it, the constants of physics are different. Atoms as we know them cannot exist. The expected time for this to happen spontaneously is astronomically long, far longer than the current age of the universe. This is not a prediction that it happens soon, but it is not on a countdown. It is a probability per unit of space, per unit of time, which means it does not build toward anything. There is no accumulation, no signal, no sequence of events that could be observed beforehand. And because the bubble wall travels at essentially the speed of light, it outruns any warning of itself. There is no image of it approaching because the light that would carry that image arrives at the same instant the wall does. If a bubble had formed anywhere close enough to reach us, the first evidence of it would arrive at the same moment as the end of it. Not a flash, not a sound. The rules holding your atoms together would simply be replaced faster than a single neuron could fire. Which brings us back to the beginning. Nothing about tonight's sky would look any different if that had already happened somewhere out there and was already on its way. Here is what makes all of this genuinely unsettling, and it is not any single scenario. It is that we cannot currently tell which one we are living in. The difference between freezing, collapsing, and being torn apart comes down to a number we have not measured precisely enough. The difference between permanence and a vacuum on a knife's edge comes down to two particle masses and an assumption that nothing unexpected waits at higher energy. Every one of these endings is consistent with everything we can currently see. The universe is not hiding this. It is simply so large and so slow and so indifferent that the question of how it ends is written in decimal places we cannot yet read. The stars will look the same tomorrow night. They would look the same either way.